Hi everyone and welcome to this lecture. In the past lecture we saw that how we can construct series solutions near singular points when uh, the roots that came in terms of r were different and they did not differ by an integer. So in this video I'm going to first consider an example where the roots will be equal, and in the second example, which we will see very schematically but not in details, they will have the roots as different roots, but they differ by an integer. That means their difference is an integer. So obviously we are considering differential equations of this form. So without further ado, let's get started solving them. And obviously we need to take an example, and this example that we're considering, this will be for this equal root case. Obviously I know it before because I solved it, and let's get started. So let's see what happens when there are two equal roots. So our example is this equation. And if you bring it in the standard form, it will look something like this. Equals to 0. Now we try a solution. Y of t sum over n from 0 to infinity, and this is just an t to the power n plus r. This is the kind of solution that we have been trying, and we already know how to do that. You need to differentiate it twice, put it over here. You need to differentiate once, put it over here. Then you need to put this whole thing over here. And if we do the algebra, after the algebra, obviously I'm not showing it right now because I already showed it in the past two videos. So to save some time, I'm going to skip the algebra and I'm going to show you the end result. The end result will look something like this. 2, there will be a sum from 0 to infinity. It will be n plus r minus 1. There will be a n t to the power n plus r minus 1 plus 2 into sum over n equals to 0 to infinity n plus r a of n t to the power n plus r minus 1. Then you'll have a minus sign over here from n equals to 0 to infinity n plus r a of n t to the power n plus r, and let me just write down the last term. This is just n equals to 0 to infinity a of n t to the power n. This is equals to 0, and again you can see that this the powers of t, they are not equal, so somehow we have to make them equal so that we can factor it out. And again we'll use the trick that we mentioned earlier, because obviously we cannot do anything with r, anything that involves r, because r is not a dumb index. The only dumb index is n, and here what we can do is that we can take m is equals to n minus 1. So that means n is equals to m plus 1. And after you are done writing these three terms, that is this one, and yeah, okay, so there is no modification needed for this one. Oops, I'm sorry, I think I did something wrong. It should be n plus r. Yeah, so only these two terms will need some modification, this won't. And if you modify this term so that instead of t to the power n plus r minus 1, this two term comes in the form of t to the power m plus r, and then you replace m with n. Obviously now if you do that, the summation won't start from 0 again like you saw in the past video, that is the previous lecture. And obviously you have to start from the appropriate m. And if you just see from here that when n equals to 0, m means minus 1, right? That's what we are getting. Or when m equals to 0, this n equals to 1. So if you do that, obviously I can show you one term at least. So let me just show this term. For this term, what is happening for this term, because both of this term have a t to the power n plus r minus 1 term. So let me just calculate and show you what will happen if you do that. So we are going to use this substitution, and after you do that, n is equals to n plus 1, we will have for the second term, this is the second term, and you will get m plus 1 equals to 0, right, to infinity. That means just m starting from minus 1. So you can write that directly, or you can just write like me, just to avoid confusion. It starts from minus 1, and then there is this n plus r, but n is equals to what? N is equals to m plus 1. So it will be r plus m plus 1. M plus r plus 1, same thing. And this n minus 1 will be replaced by n minus 1 will be replaced by m. So let's write a of n, but n is equals to again m plus 1, so this will be just a m plus 1, and this will be t to the power m plus r, right? But here the summation is starting from minus 1. So again we need to replace m, it goes to n, that means replacing. This is the replacing part, and after you replace this, you will have n is equals to minus 1 to infinity n plus r plus 1 a of n plus 1 t to the power n plus r. And if you want to start from n equals to 0, you need to evaluate it, that is this form or this term over here, for n equals to minus 1. So if you have to, if you are done with that, that means if you are doing that, you will have this inactive sum. Also these are called inactive sum because we are not summing it and getting the result. So this inactive sum will be there, and it will be again n plus r plus 1 a into n a underscore n plus 1 t to the power n plus r, plus when n is equals to minus 1, this is just r a of 0 t to the power minus r, something like this, right? So oh sorry, it shouldn't be minus r, I'm sorry, my mistake. It should be rather n is equals to minus 1, so that will be just 1 minus 1 plus r, or r minus 1. So let's write it as r minus 1. And similarly for the first term, you need to do the same thing that I did here for the second term. And if you do that and you are done with the algebra, that means all the replacing thing, then all the switching these dummy variables, you will have something like 2 r square a0 t to the power r minus 1 plus some n from 0 to infinity. And let me just write out the terms because it's pretty big expression. So 2 n plus r plus 1 whole squared a of n plus 1 minus n plus r minus 1 a of n, and here you will have a t to the power n plus r. And like before, we are going to demand this guy to be 0, and we are going to have a recursion from this by demanding it to be 0 as well. So demand this is also 0, and this will turn out to be a recursion relationship, and this will give us the roots. So if you just put this term, that is 2r square a0 t to the power r minus 1 equals to 0, and you demand also that t is not 0, because t is equals to 0 means the trivial solution, right? So you will get r square equals to 0, and obviously a naught is also 0. Sorry, a naught is also not 0, that is this thing, and also t is not 0. So this means r is equals to 0, and the two roots are just a simple root with multiplicity 2, and we will see what happens when this is the case. And by demanding that this series terminates, as I mentioned in my previous lecture, that this summation from this summation you will have a recursion relation like this. So the recursion will give us the following, that is a of n plus 1 is equals to n minus 1 to n plus 1 whole square, and we are putting the r's value to be 0 over here. Obviously you have to first evaluate it, because you can see that there is a n plus r plus 1 and there is a n plus r minus 1. So I already know that there are two roots, however both of the roots are same, and that is r equals to 0. So to simplify things, you put r equals to 0, so this is just n plus 1 whole square that goes in the denominator, and this is the numerator, n plus r minus 1, but r is equals to 0, so this is just n minus 1. So that's why I have written here n minus 1, and in the denominator it's n plus 1, 2n plus 2 into n plus 1 whole square, and obviously there is this a of n. And now you are going to calculate the terms that is coming from this recursion relationship, but you can see that this will yield not yield the a0. So what we can do right now, since these a's are our arbitrary constant, what we can do, so for simplicity we take a0 to be 1, and obviously this is an arbitrary choice. This is an arbitrary choice. The reason being, when you start from n equals to 0, you will have a1 in terms of a of 0, and then you will have n equals to 1, and that will give you a2 in terms of a of 1, but a of 1 itself is given in terms of a of 0. So a of 2 is also given in terms of a of 0 as well. Similarly it goes for the higher terms, that is the a3, a4 and all that. So we are just going to take a0 is equals to 1 to have a very simple or let's say it makes the mathematical manipulation simple. Obviously you can take any number you want, because that thing is arbitrarily chosen. And now when we take this, we can see that our terms that are coming from this recursion is something like this. So we are calling it, let's say a1 will be it will be for n equals to 1. So if you put n equals to 1 over here, this is 0, right? Sorry, a1 sorry, this should be a 2, not 1, because we are considering n equals to 1, and this is just 0. So that's a bummer. Why? Because if a2 is 0, then if you want to calculate a3, it will come in terms of a2, right? And then if you want to calculate a4, that is n equals to 3, let me just show you what happens. So this a2 is 0, so when you to put n equals to 2, what happens? You will have a3 in terms of 2 minus 1, 2 into 2 plus 1 whole squared times a2, but a2 is 0, so a3 is also 0. Similarly a4 will be 0, a5 will be 0, and all that. So you can see that all the terms are getting eliminated. So this yields a very simple solution, and obviously it doesn't have to do anything. It doesn't have to do anything with this a0 is equals to 1. It's because of the nature of the nominator, that it has something n minus 1, and the recursion that gives us the n plus 1 is equals to some number times a of n. So since all the terms are getting 0, we will end up having a solution that will look like a1 that okay, let's call this solution y1, and it will look something like this, 1/2 of t, right? Because when you put n equals to 0, that is starting from n equals to 0, right? So that means your n equals to, when you put n equals to 0, a1 is just, there will be a -1 on the nominator when n is equals to 0, and in the denominator there will be just these two, and this is just 1 square, that is 1, and there will be a a0. So, and we are taking a0 to be 1, so that's why I'm getting this 1 minus 1/2 of t, this solution. Now, since this is a second order differential equation, we expect a second solution. And if you recall that in the previous video we saw that there were two roots, and because of those two roots we got two different recursion relations, and we had no problem in building the other solution. But here we have only one root, but it's repeated 2 times, so that's why we're getting only one recursion, and we were able to build only one solution. And to build the second solution we need to have a have something else, and that is given by a theorem. And I'm not going to prove the theorem, we are going to just accept it without any proof. That is, the second solution is given by y2 of t is equals to y1 of t ln of t plus, there will be a t r0, this is the repeated root. For our case this is 0, but we'll construct that special case later, and this is the general case because this is a theorem, right? r0 sum over n equals to 1 to infinity b of n t to the power n. So in our case, that is for this example, we already found what is y1, and the r0 is just 0, so y2 of t is just y1 of t ln of t plus sum over n equals to 1 to infinity and bn t to the power n. This is your second solution, and the general solution is just c1 y1 c2 y2. That's it, you're done. However, this theorem, that is this guy, sorry, yeah, it seems a bit weird, sorry. So this theorem will work supposing that t is equals to 0 is a regular singular point of the equation, that is the differential equation we are considering, and the functions t q divided by p and t square r divided by p around t is analytic. That means all the assumptions that we started with in 2 lectures back. So that's the case it will work only. And you might ask that is there any proof for this theorem? Yes, there is, but we're not going to consider it. So obviously there is another way to actually see that this is the kind of second solution that will come up, and that is, if you want to construct a second solution, what you need to do is just let's say this is your trial function now, that you are trying this and you want to see whether this will work. You just put it back in the differential equation. That's like working backwards, that is on here, and this should work. So this is what one needs to do when there is repeated roots. First one needs to construct one solution, and then the other solution will be given by where was that? Sorry for scrolling too fast. Yeah, I think I went down a bit further. Yeah, so if you can construct this first solution y1 of t, the second solution is constructed with this theorem, with the help of this theorem. And now we are going to see some cases where we'll have equal roots. So let me just get rid of the writing that was done over here. Yeah. So this is our last case for the series solution. This is where the roots differ by an integer. And again, we'll start with an example. So the example equation that we're going to take will be something like the following. That is, let's take the example of t square y double prime plus t square y prime minus t plus 2y equals to 0. And obviously you need to put the solution in the form of this summation. Obviously I'm not writing the limits, a n t to the power n plus r, and this obviously okay, fine. So let's write the limit, and these are the limits. So this is the thing you need to put over here with these appropriate differentiations, and then you need to do that m equals to n plus 1 or n minus 1 trick, and you need to replace them again with n, and you need to finally merge them together. And if you do that, that is after a big algebra. I'm not doing the algebra here, but it's the same as we have been doing for the past 3 lectures. So after the big algebra, what you'll have is that the final result in terms of this. Let me just write them down. Oops, sorry, I think I made a mistake. Sorry for that. There should be a n equals to 1, it shouldn't be 0. So let me just rewrite this term, the second term, that is. So as you can see that handling this lengthy algebra is pretty tricky, and you need to be really careful when you do this kind of things, otherwise the whole thing will be a mess. So this is starting from n equals to 1 to infinity, a of n minus 1 t to the power n plus r minus 2 n equals to 0 to infinity, a of n t to the power n plus r equals to 0. And now you have to simplify all these things again. So by simplifying, I mean you can see that there is this n equals to 1 thing, and there is this n equals to 1 thing. So you need to work with this term and this term, that is the second term and the third term, and you need to evaluate it for n equals to 1 and push the summation to start from 0. So if you do that like we did in the past 2 examples, you will have an equation like this. This will be a bit big, so please have patience. And there will be this a of n, that means this is the guy that is appearing in front of a of n, and there will be more terms minus Oh, sorry, this will be a plus, not a minus. So yeah, I was right before. As you can see, this is already taking me really long just to type it. So just imagine how much time you have to spend calculating all this. Again, this is the term. Again, we put this guy to be 0, that's the demand. So this gives us the roots and this gives us the recursion. So the roots equation turns out to be r minus 2 a0 is equals to 0. Again, a0 is not 0 because that would be just trivial, and this r square minus r minus 2 equals to 0 gives two roots as, let's call them r1 and r2, and one of them is just 2, one of them is just minus 1. Okay, that's done. And if you evaluate this recursion relationship, that is the guy over here, you will have, let's say you are making this to be 0, right? So you will have something like a very big expression, obviously. So just be a bit patient. I'm writing it down, a of n minus 2, or obviously you can set a of n over here. So a of n, and what was the term that was in front of a of n? This guy, n plus r minus 1 minus 2. So this will go down in the denominator, third bracket, n plus r minus 1, I think, minus 2. Yeah, and then you have n plus r minus 2 a to the a of n minus 2. So n plus r, oh my god, n plus r minus 2 a of n minus 2, and these two terms had a plus between them, and since we demanded to this guy to vanish somewhere, there will be a minus sign over here because it's like x plus y equals to 0, so x is equals to minus y. And now you have two roots, r equals to 1 and r equals to 2, and we also have this a naught thing. So another assumption we're going to take right now to simplify our life is that a0 is equals to 1, and now in fact this can be even made even simpler, because you see these two terms are on a term with multiplication with each other. That is, what you can do is that you can multiply these two sides and simplify the result. So if you simplify, what you'll have is that a of n is equals to minus n plus r plus 1 in the denominator, sorry, and you will have a of n minus 1 over here. And obviously this, when you do the simplification, that is you multiply these two things, you factor a n plus r minus 2 out, what you need to assume is that this n plus r minus 2, this is not 0, because that's why you could factor it out in the denominator. So n plus r minus 2 is not equals to 0. This is another assumption. So again, this is our relationship, the recursion relationship. Now let's consider the case where r is equals to 2. That means r1. So we're considering the case r1 equals to 2, and this will yield an is equals to minus 1 by n plus 3 a of n minus 1, right? Where n is equals to 1, 2, 3 and etc. Because we already took n's when n is equals to 0, that means a0 is equals to 1. So n is equals to 0 case is already being considered, so it will be n equals to 1, 2, 3 and all that. So a0 is equals to 1, a1 will be minus 1 by 0, 1 plus 3, a1 minus 1, that means a0 minus 4, a0 is 1, so this will be just minus 4, and you can obviously calculate all the terms like this. A2 will be, I'm not showing you the calculation because this is pretty easy, this is just 1 by 20, and so on. So the first solution will have y1 of t. Recall that the solution was in the form of sum over a of n, t of n plus r, right? Or you could also equivalently write it as t to the power r, summation of a of n, t of n. And if you write that, this will be just t to the power 2, because here we are considering r1, that is 2, so there will be t square, and there is this summation that starts from 0 to infinity, a of n t to the power n. So if you expand this out, this will look like a0, a1, t, a2, t square, and so on. So now put the values of these a's. So this a0 was taken to be as 1, a1 was minus 1 by 4, so this is just t by 4, a2 was 1 upon 20, that means plus 1 upon 20. So yeah, this is how it will go. There might be a minus n over here or a plus n over here. So this is the solution, that is, this is the first solution. Now what about a second solution? So to find this second solution, we need to set r is equals to minus 1. So we have built the first solution, let's try to build the second one. So we are going to take the second solution, we are trying to build the second solution, and this time we are going to take the second root, that is r2 is equals to minus 1. And if you recall that we had something like this, n minus r plus 2, before we obtained the recursion relation for r is r1, that is the when r was equals to 2, but this time we have r2 is equals to minus 1. So this will mean that n plus r plus 1 a of n plus a of n minus 1, this is 0, right? But if you put r equals to, that means r2 equals to minus 1 over here, what you will end up having is that n minus 3 times n into an. So this is just putting the value over here, and that's the result on the second line. So you will have n a of n plus a of n minus 1 equals to 0 for n is equals to 1, 2, 3 and order. Because a of 0 is already decided to be 1, that's what we took. Now this says that n is equals to 3, or n is equals to minus a of n minus 1 divided by n, right? That's what it tells us. So this looks like a recursion relationship, and if you evaluate the terms, that means if you don't focus on this n equals to 3 and you try to evaluate this thing, something wrong happens. Let me show you what. That is, a0 is 1, that's something we assumed, or let's say we took to make our life simpler. And a1, if you calculate these things, it will just be minus a0, that means it's just minus 1, right? a2 will be minus a2 will be just 1/2 of a0, that means 1/2. However, when n equals to 3, let me write it down because this is the part that is subtle. So when n equals to 3, we are seeing that we are getting some value from this equation over here, right? That means this one, when n equals to 3. So this yields some value when n is equals to 3. However, if you look at the origin of this recursion, that is this guy over here, it says that when n is equals to 3, this part is 0. So back at that moment, this, even if it gives you some value, let's say you are considering something like this whole thing is something 0 divided by n minus 3, that becomes an indeterminate form. It becomes a 0 times 0 thing. So even if you don't want to think like this, which is not the proper way to do things, when n is equals to 3, this becomes 0, there is this expression, and multiplying 0 with this thing is 0, and it says 0 equals 0 thing. So at that point, this recursion that is written over here, it doesn't make any sense. It doesn't apply at all. So that's the problem. So when n equals to 3, this recursion doesn't apply at all, because the very origin of the recursion gets destroyed. So that's the thing that has been happening. Alright, so this A3 term is something we called undetermined, but not in the sense that it becomes a 0 by 0 thing, but it's rather arbitrary, because if 0 is equals to 0, if you are familiar with the row reduction that we talked in the first week, whenever you have a 0 equals 0, and that means there is an arbitrary freedom. That means there can be many solutions. So we say that this A equals to 3 term, A3 term is arbitrary. So we cannot possibly find a value for this A3. Okay, but we are fine to find A4 because we found A1, A2. So we won't be calculating this A3, rather we'll take it as A3 is something arbitrary. However, we can find this A4 using this formula over here, because when n equals to 4, nothing goes wrong over here, because this becomes 1 and this guy can be 0. So when n equals to 4, we will find something like 1 minus 4 A3. This is the subtle part, because you can see that this recursion is saying you a of n is equals to minus a of n minus 1 divided by n. So when n equals to 4, this becomes 3, right? And again you can go for a5. However, a5 will come in terms of a4 as well. This will just be 1 by 5 a4, but a4 is in terms of a3, right? So you will have this 1 by 20 a3 thing. Similarly, a of 6, this will just be minus 120. If you do the calculation, you will find this out. This will be minus 1 by 120 times a3. And finally, this a3 is not determined. That's what we mean by undetermined, and it's arbitrary, that I'm not choosing a specific value for it. So finally we write the solution. The second solution, that is as T inverse A0 1 minus t plus t square by 2. This is, you see this, why am I writing this? Because again the solution was in the form of t to the power n plus r a of n. That's why I'm just expanding this out without any detail. So the detail is pretty simple. So you just have to express this summation, that's it, nothing else. And then all the rest of the terms are coming in the form of, oh yeah, there should be a bracket over here, and all the rest of the terms are coming in terms of a3, because you can see that these were the terms. So this is the 0 term, this is the n equals to 1 term, this is the n equals to 2 term, this is the n equals to 3 term, okay, where a3 t3 comes. So this is t3, and then you have the 4th term, 5th term, 6th term, all that. So this is just 1 by 4 t to the power 4 plus 1 by 20 t to the power 5, and so on. And we can multiply this whole expression with this t inverse, that is t to the power minus 1, and this will turn out to be nothing but a0 t inverse 1 minus 1 plus 1/2 of t, and there is this a3 and this series thing. However, note that in the first solution, this was our this is our first solution. That is the thing, right? We got at first. And if you look at this series over here, that is this part, you can take a t square common or factor it out, and you can easily recognize this is nothing but y1. So let's write y1 of t like this. Okay, and this is in fact the full solution, and this part is nothing but the second solution. So it points us towards the fact that, let me just go down a bit. So in case you are lost by all these computations, so let me give you a summary. When these roots are distinct and they differ by an integer, and when they differ by an integer, what you need to do first is that you need to construct one solution first. Let's say you are constructing a solution for, the first step is to construct a solution. Construct a solution for one of the roots. Let's say you are taking this R1, and then the second solution is nothing but y2 of t, cy1 of t plus, there will be a ln t as well, ln of t plus t to the power r2, then there is 1 plus sum over n equals to 1 to infinity b of n t to the power n. Again, these b's are the coefficients that you calculate, and this c is a arbitrary constant. So all you need to do is to find this y1, and then can use this formula to construct the second solution. And this also comes from a theorem like we did for the equal root part. So this will be it for today, and I'll see you guys in the next lecture. Thank you.